So at this point, we have four separate equations which are describing the behavior of gases. And that can be a little bit overwhelming to try and figure out, oh my goodness, I have four equations that I have to remember. I'm going to have to try and figure out in what case I use each equation. So I'm kind of wondering if maybe we can just take a moment to potentially combine all of these variables into one mega equation and make our lives just a little bit easier. So at this point, these are the four equations that we know. We have Boyle's law, Charles' law, Gay-Lussac's law, and then we have Avogadro's law down at the bottom. So let's just start at the very beginning with Boyle's law. We notice that pressure tends to be multiplied times volume. But then in the next two equations, I see that volume is divided by temperature, but so is pressure. So I wish that if we could just kind of take this temperature and kind of combine it down with pressure, volume, and temperature all together at the same time. And in fact, we can. And we can kind of make this into one mega equation where we have P1 times V1 divided by T1 equals P2 V2 divided by T2. This equation is known as the combined gas law, and it's only specifically used when you have changing conditions inside of a problem. And what's even cooler about this law, you only have to remember this one law, but you can derive all three of these minor gas laws back from it. Key thing to remember here, Boyle's law ironically holds temperature constant. So if you just cover up temperature from this combined gas law equation, look at the law that pops back out. It's Boyle's law. Charles' law holds pressure constant. And if I do the same thing, just kind of cover up pressure, notice how Charles' law comes right back out. And then finally, Gay-Lussac's law occurs under conditions of constant volume. So if I would cover up the volume, you get Gay-Lussac's law right back out. You can do any calculations that you would need to with any particular problem. So I think that the combined gas law for us has some value, and in and of itself, it can actually solve a multitude of additional chemistry problems. You're going to see that actually at the end of this video. I have a sample problem for you. Now we only have one more equation left to smush in here. So let's take a look at this Avogadro's law. Now although this is the way that it was written that we kind of use in other problems, remember that because they're directly related, that would be moles and volume, it really doesn't matter which variable we divide by which variable. So I'm going to reorganize it. Instead of n divided by v, I'm going to take a look at v divided by n, only because of how I have my equation up top set up. Now, it's almost as if moles gets divided by volume, so I'm wondering if I can just take that number of moles and kind of push it next to the temperature, and that would be P and then V and then T and N on the bottom. So before we get any further, I just kind of want to remind you of a couple different things. That when we were learning about the minor gas laws, pressure times volume provided us with a constant. Pressure divided by temperature provided us with a constant. Volume divided by temperature provided us with a constant. And volume divided by moles, or moles divided by volume, provided us with a constant. If that's in fact true, then P times V divided by N times T should also equal a constant. And it in fact does. Now, that's really, really important because I honestly can't really measure anything else about a gas. Pressure, volume, moles, and temperature are essentially the limit of the number of measurements that I can take. And that means that that constant is going to be constant, 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 constant. I mean, there is no other constant in the world, so to speak. So that constant, we're going to give a special letter and a special name. We call this constant the universal gas constant. And since that's a pain to write over and over and over again, we condense that back down to a letter, which is known as R. I don't know why they picked R, but it is R. This has one distinct value, and again, it is a constant. It is equal to 0.08206 with a very weird unit. Liters times atmospheres divided by Kelvin times mole. Now, what's nice about that unit is it does remind you of the units that you're allowed to use for volume, for pressure, for temperature, and obviously for moles as well. Your volume must be in units of liters, your pressure must be in units of ATM, your temperature must be in units of Kelvin, and moles, of course, has to be in moles. Now, I don't really quite like the look of this equation yet. It's a little awkward with some combined units and all the division. I like to see a nice clean multiplication style equation. So I'm just going to multiply the n and the t over to the opposite side of the equation to kind of clean this up a little bit. And we're going to present it like this. PV equals nRT. This is the form of the equation that you're going to see most often in textbooks. I lovingly refer to this as PervNerd. It's a kind of an easy way of remembering the equation. The real name of the gas law is called the ideal gas law, and this is only used under constant conditions. So you're not able to change the conditions within the problem. It's only for constant. And the most important thing to realize here is the moles part of this. This is really and truly the only equation which allows us to calculate over to moles. And in that case, this is going to be our stepping stone back into stoichiometry with gases. More on that later. Let's take a look at some example problems so we can kind of get you started. One big reminder before we keep moving. The units on are 0.08206. They're liters, atmospheres, divided by Kelvin mole. It is extremely important that before you go and plug and chug with any numbers in this chapter, you have to convert into those specific units or you will not meet success with your problems. Here's sample problem number 1. A sample of a gas is placed in a container with a volume of 2.7 liters. The pressure is measured at 1.25 atm at a temperature of 295 Kelvin. How many moles of gas are in the container? Now, the first thing that I notice here is that the conditions are not changing. There's no squeezing of the container or heating of the container or escaping of a gas or anything like that. So they're under constant conditions. What that means is that for this particular problem, I can use PV equals nRT. The next step of my problem then would be to define my variables. I'm just going to kind of scan through and find some of my numbers. The first one I see is 2.7 liters, so I'm going to go ahead and define him as V. I see 1.25 atms, that's a pressure. 295 Kelvin, that's a temperature. And then finally the problem asks me to solve for the number of moles. That's what we would plug in for N. And since that's not defined in the problem, I'm going to define it as X. It's time to plug my variables back into the problem, which should look a little something like this. P times V equals nRT. Now I didn't put the units on my R because I was kind of concerned about the screen space, but you should always present those units. Time to chug these numbers back into my calculator and solve for that X. And when I did, I limited my answer to 2 significant figures, because the fewest number of sig figs that I have would be my volume at 2.7 liters. X ultimately equals 0.14 moles. Not that bad as long as you keep track of all of your units and recognize that the conditions are not changing inside of this problem. Let's take a look at sample problem number 2. It's a little bit wordier. A sample of a gas is placed in a container with a volume of 2.7 liters, a pressure of 1.5 atm, and a temperature of 295 Kelvin. If the temperature is raised to 325 Kelvin and the volume is reduced to 1.0 liters, what will happen to the pressure inside the container? Now, as I'm reading, I'm struck by one phrase, and that is this: the temperature is raised. What that means is that the conditions are changing on the inside of this problem, which is my cue that I need to use the second of the 2 equations that we just went over, and that would be the combined gas law. P1 times V1 divided by T1 equals P2 times V2 divided by T2. Time to start to look at my variables and to decide kind of what they're going to go in for in my problem. Now, generally speaking, once you define where this change is taking place, you can usually take the numbers on the first half of the problem as your 1s and the second half of the problem as your 2s and plug and chug kind of easily that way. But again, always better to define them as you're going along. First number I see is 2.7 liters. That's the first volume that I see, so that's going to be V1. 1.5 atm, that's my first pressure, and 295 Kelvin is my first temperature. Then after it mentions that temperature is raised, those conditions were changed, then we can start defining our second set of variables, our 2's. T2 is 325 Kelvin, V2 is 1.0 liters, and then finally the problem asks me to solve for pressure, so that must be my P2. Since it's undefined, I'm going to allow that to go in as X. I'm going to plug these variables back into my equation, which, yes, is a little bit larger and is going to require a little bit more algebra. But once you do, scan all of the variables, find the one with the fewest sig figs. That would be either 2.7 or 1.0 or 1.5. All of those have 2 sig figs. My answer should only have 2 significant figures, and that would leave me with 4.5 ATM.